Picture the very last moments of existence, the stars fading into darkness, the fabric of space itself tearing apart, or perhaps everything collapsing back into a single, unimaginable point. How will the universe meet its ultimate fate? It's a question that's haunted scientists, philosophers, and dreamers for centuries, and today we're diving into the deepest mysteries of cosmic endings. The universe isn't eternal, it had a beginning, and one day it will have an end. But what that end looks like, well, that's where things get truly fascinating and terrifying. Across billions of years, galaxies drift apart, stars burn out, and even the fundamental forces that hold reality together might one day unravel. Some endings are slow and quiet, like a universe fading into infinite cold and silence. Others are violent and sudden, where space itself is ripped apart in a catastrophic finale. And then there are the possibilities so strange they sound like science fiction. Black holes devouring everything, vacuum decay rewriting the laws of physics, or even the birth of a brand new universe from the ashes of our own. In this journey, we'll explore 25 chilling ways the cosmos could meet its doom, from the hauntingly peaceful heat death to the explosive Big Crunch, the terrifying Big Rip, and beyond. Each scenario is a reminder of just how fragile our cosmic home really is, and how much we still don't understand about the forces shaping existence itself. So buckle up, this isn't just a tour of the universe's final moments. It's a chance to witness the ultimate fate of everything and to ask the biggest question of all: what legacy will the universe leave behind when time itself runs out? The first and perhaps the most haunting possibility is the heat death, a slow but inevitable march toward absolute stillness. Imagine a universe where every star has burned out, every black hole has evaporated, and even the last whispers of energy have dissipated into endless cold. No light, no heat, no life, just an infinite void where time itself becomes meaningless. This isn't science fiction. It's the ultimate fate predicted by the laws of thermodynamics when entropy finally reaches its peak. Entropy is the universe's way of measuring disorder, and it always increases over time. Picture a cup of hot coffee left on a table. It doesn't stay hot forever. The heat spreads out, warming the air around it until everything reaches the same lukewarm temperature. Now zoom out to a cosmic scale. Stars, galaxies, and even the remnants of matter act like that coffee, radiating energy until there's nothing left to give. Over trillions upon trillions of years, every source of heat and motion will exhaust itself, leaving the universe in a state of perfect equilibrium, a frozen, featureless expanse where nothing ever changes again. Black holes, once thought to be indestructible, won't escape this fate either. Thanks to Hawking radiation, even these cosmic titans will eventually evaporate, releasing their final bursts of energy before vanishing entirely. Protons, the building blocks of atoms, might decay over unimaginable timescales, erasing the last traces of solid matter. What remains is a sea of particles so spread out that they might as well not exist at all, a universe so empty and cold that even the concept of emptiness loses meaning. The heat death isn't sudden or dramatic. It's a whisper, not a bang, but that's what makes it so unsettling. Unlike other cosmic doomsday scenarios, there's no escape, no reversal, no second act. Once the universe reaches this state, it's game over forever. No new stars will ignite, no new life will emerge, just endless darkness stretching into eternity. And yet, in this bleak vision, there's a strange kind of beauty. The heat death is the universe's final act of surrender, a quiet acceptance that even the greatest stories must one day end. But the true horror of heat death isn't just the cold or the darkness, it's the sheer, unfathomable loneliness. In this lifeless void, even the concept of time breaks down. Without change, without motion, there's nothing to mark its passage. Seconds, years, eons, they all blur into a single, endless moment. Philosophers and physicists alike grapple with this chilling idea. a universe where nothing happens forever. No stories, no observers, no memory, just an infinite expanse where the word "when" loses all meaning. And yet there's a bizarre twist hidden in this cosmic oblivion. Quantum mechanics suggests that even in a dead universe, random fluctuations could, given enough time, spark brief, eerie flickers of order. Enter the Boltzmann brane, a hypothetical self-aware entity that forms purely by chance from these fluctuations. Picture a lone consciousness suddenly blinking into existence, surrounded by nothingness, only to vanish again into the void. It's a haunting thought that the last trace of awareness in the universe might not be a civilization or a god, but a disembodied mind with no past, no future, and no one to witness its existence. Some theories go even further, suggesting these fluctuations might accidentally recreate entire universes. A random quantum blip could, in principle, birth a new Big Bang, a cosmic reset button. But the odds are so astronomically low that it's less a hope and more a statistical ghost. For all practical purposes, heat death is final. No rebirth, no cycle, just silence. What does it mean for us then, knowing this could be how everything ends? There's a strange poetry to it. All our struggles, our art, our love, every human story would leave no trace in a universe that's forgotten even itself. But perhaps that's the point. If the cosmos is fated to fade into nothing, then the only meaning that matters is the one we make right now. Heat death doesn't just erase the future, it makes the present infinitely precious. If the heat death is the universe fading into silence, the big crunch is its apocalyptic scream, a violent reversal of everything we know. Picture this: after billions of years of expansion, gravity finally wins. Galaxies stop drifting apart and begin rushing back toward each other, pulled by an irresistible force. Space itself contracts, temperatures soar, and the cosmos collapses inward like a deflating balloon. In the end, all matter, energy, and even time itself are crushed into a single, infinitely dense point, a mirror image of the Big Bang but in reverse. This isn't just poetic doom, the math actually checks out. Whether the big crunch happens depends on a cosmic tug of war between dark energy, which drives expansion, and gravity, which pulls everything together. Right now, dark energy is winning, but what if its influence weakens over time? Or what if there's enough mass in the universe to eventually overpower it? Suddenly, the fate of everything flips. Distant galaxies would blue shift as they barrel toward us, their light compressing into higher energies. The night sky would grow brighter and hotter until the last stars are ripped apart by tidal forces. Even black holes would merge into monstrous singularities, swallowing entire clusters of matter in their final moments. The most intriguing part: some theories suggest the big crunch might not be the end. Instead, it could be a reset, a cosmic reboot. Imagine the singularity at the crunch's core becoming so unstable that it triggers another Big Bang, birthing a brand new universe. This is the cyclical model, an endless loop of expansion and collapse where each iteration has slightly different physical constants, creating infinite variations of reality. It's a tantalizing idea that our universe might just be one page in an infinite cosmic storybook, but there's a catch. For this cycle to work, the conditions of each rebirth would need to align perfectly. Too much matter and the next universe might collapse immediately. Too little and it could expand into oblivion. And even if the cycle continues, there's no guarantee the next universe would support life or even recognizable physics. The big crunch could be less a phoenix and more a roll of the dice, with existence itself at stake. What's eerie is how differently time would behave in those final moments. As space contracts, the universe's clock would appear to speed up from our perspective. The last stars would explode in rapid succession, black holes would evaporate in flashes, and the final collapse might feel instantaneous, a blink between existence and oblivion. There'd be no time to reflect, no grand farewell, just a sudden, violent return to the singularity where it all began. The Big Crunch forces us to confront a profound question: is death the end or just a transformation? If the universe can recycle itself, does that make our existence more meaningful or less? Unlike the cold, eternal silence of heat death, the crunch offers a glimmer of continuity, but it's a fragile hope balanced on the knife's edge of physics. And whether the next universe remembers ours or even follows the same rules remains one of cosmology's greatest mysteries. The final moments of the Big Crunch would be a spectacle of unimaginable violence, a cosmic demolition derby where everything we've ever known is shredded into oblivion. Picture galaxies once separated by millions of light years, now hurtling toward each other at blinding speeds, their spiral arms tangling in a grotesque dance. Stars collide like fireworks in slow motion, their cores ripped apart by gravitational tides as temperatures soar to trillions of degrees. The night sky, once a serene tapestry of distant lights, becomes a blazing furnace, a single, searing point of light growing brighter by the second. Space itself would warp and twist under the strain, bending until the very fabric of reality begins to crumple like paper in a fist. Time, no longer a steady river, becomes a chaotic torrent. Events that once took eons now unfolding in seconds. Black holes, the last survivors of this cataclysm, swallow entire constellations before merging into gargantuan singularities, their event horizons stretching across what little remains of the universe. Even the fundamental forces of nature start to break down: electromagnetism, the strong nuclear force, all compressed into a screaming singularity where the laws of physics as we know them cease to exist. It's a haunting mirror of the Big Bang, but where that event burst outward in creative chaos, the crunch is destruction in reverse. The Big Bang scattered matter across the void, the crunch drags it all back into the abyss. The bang was a churning sea of particles congealing into structure. The crunch is structure unraveling into pure, formless energy. And where the bang birthed time itself, the crunch devours it until the universe's final tick, when the clock stops forever. What would it feel like to witness these last moments? If anything could survive to see them, gravity would stretch and compress matter like taffy, tidal forces tearing apart planets and stars alike. The cosmic microwave background, the faint afterglow of the Big Bang, would blue shift into deadly gamma radiation, bathing everything in lethal energy. For any hypothetical observer, the entire history of the cosmos would replay in fast-forward: galaxies rushing closer, stars igniting and exploding in seconds, until the entire visible universe fits inside a single, shrinking horizon. The eerie beauty of this scenario is its symmetry. The universe might end as it began, not with a whimper but with a roar. But where the Big Bang was a beginning without a past, the crunch would be an ending without a future. No after, no memory, no trace, just an infinite density where all stories, ours included, are compressed into a single, silent point. Now imagine a force so powerful it doesn't just slow the universe's expansion, it accelerates it beyond control, shredding reality itself apart atom by atom. This is the Big Rip, a cosmic doomsday where dark energy doesn't merely win, it goes rogue. Unlike the slow fade of heat death or the violent collapse of the Big Crunch, the Big Rip is a crescendo of destruction, a moment when the fabric of space-time tears like paper under unimaginable strain. Dark energy is the mysterious force pushing galaxies apart faster and faster, but in this scenario it doesn't stay constant. Instead, it grows stronger over time, evolving into something called phantom energy. Picture a car's accelerator stuck to the floor. The universe doesn't just expand, it hurtles toward oblivion with ever-increasing speed. First, galaxy clusters are ripped apart, their gravitational bonds no match for the escalating force. Then, individual galaxies unravel, stars wrenched from their orbits like beads scattering from a broken necklace. But the horror doesn't stop there. As phantom energy intensifies, even solar systems are torn asunder. Planets are yanked away from their suns, their orbits stretching like taffy until they snap. Then comes the gut-wrenching finale. The very fabric of space itself stretches faster than the speed of light, severing the bonds holding atoms together. In the last milliseconds, stars, planets, and even molecules are ripped apart, protons and electrons torn so far apart they can never interact again. The universe isn't just dying, it's being disassembled piece by piece down to the quantum level. The countdown to the Big Rip isn't measured in billions of years. It could happen in a cosmic blink. From the moment phantom energy dominates, the end game accelerates. In the final hour, gravitational forces crumble, planets fracture, and the night sky fills with the light of trillions of dying stars. Then, in an instant, space-time itself reaches a breaking point. There's no black hole, no singularity, just emptiness where reality used to be. What makes this scenario uniquely terrifying is its inevitability. Unlike the Big Crunch, which depends on gravity's resurgence, or heat death, which plays out over eons, the Big Rip could be triggered by a slight tweak in dark energy's behavior, a shift we might not detect until it's too late. And unlike other cosmic endings, there's no poetic symmetry, no rebirth, just an endless, empty expanse where not even atoms remain. The Big Rip doesn't just end the universe, it erases the very concept of existence. The final split second of the Big Rip isn't just destruction, it's the unraveling of reality's deepest foundations. Picture this: after galaxies, stars, and planets are torn apart, the phantom energy's grip tightens on the fabric of existence itself. Molecules, once bound by electromagnetic forces, are wrenched into individual atoms. Then, atoms fracture nuclei, shattering like glass as even the strong nuclear force, which holds protons and neutrons together, is overcome. But the horror doesn't stop there. In the last microseconds, quarks, the fundamental particles that make up protons and neutrons, are ripped from one another. It's as if the universe is being peeled apart layer by layer, down to the very building blocks of matter. This raises a chilling question: can space-time itself survive such a rupture? Some theories suggest that once phantom energy reaches infinite strength, it wouldn't just tear matter apart, it would shred the fabric of space-time, snapping the cosmic stage on which reality plays out. Think of space-time as a rubber sheet stretched too thin until it splits. If this happens, the concept of where and when would cease to exist. No more distances, no more moments, just a formless void where physics as we know it has no meaning. But not all physicists agree. Alternative models propose that space-time might endure even in a mangled state. Imagine a tattered net full of holes but still holding some frayed threads. In this scenario, the universe wouldn't vanish. It would become a fractured, nonsensical realm where causality breaks down. Time could loop, dimensions might crinkle, and the laws of physics could vary wildly from one Chinese letter patch to another. It's a fate arguably stranger than pure annihilation. The debate hinges on the true nature of dark energy, a mystery we've barely begun to unravel. If phantom energy behaves like a true singularity, growing infinitely strong, then the Big Rip isn't just an end. It's an erasure of the rules that make endings or beginnings possible. But if space-time somehow persists, even in a broken form, the universe might linger in a state beyond our comprehension, a ghostly afterimage of existence where even the word universe no longer applies. What makes this scenario uniquely unsettling is its intimacy. Unlike the distant collapse of a Big Crunch or the slow fade of heat death, the Big Rip could dismantle reality at every scale simultaneously, from galactic superclusters to the DNA in your cells. There's no hiding, no distant corner left untouched. In its final moments, the universe wouldn't just die, it would dissolve. If the Big Rip tears the universe apart from the outside, vacuum decay annihilates it from within, an invisible apocalypse born in the quantum realm. Imagine the very ground beneath your feet, the air you breathe, the stars in the sky, all built on a lie. That's the nightmare of false vacuum theory. Our universe might not be in its most stable state. Instead, it could be perched precariously on a quantum ledge like a marble balanced on the edge of a bowl. One nudge and it tumbles into a lower energy state, a true vacuum, where the laws of physics as we know them cease to exist. This isn't just theoretical. The Higgs field, which gives particles their mass, might exist in a false vacuum, an unstable equilibrium. If a tiny patch of space somewhere in the cosmos quantum tunnels into the true vacuum state, it would create a bubble of rewritten physics. That bubble would expand at the speed of light, its walls a wave of annihilation. Everything it touches, atoms, forces, even space-time itself, would be reconfigured into something unrecognizable. One moment you're sipping coffee, the next the very particles composing your body no longer interact in ways that allow chemistry, let alone life. The trigger could be anything, a random quantum fluctuation, a high-energy particle collision, or even the natural decay of the false vacuum over trillions of years. There'd be no warning. The bubble's edge moves at light speed, so by the time you see it coming, it's already erased you. Worse, this process could already be underway somewhere in the cosmos. A single bubble born in some distant galaxy might be racing toward us right now. What's chilling is how clean this apocalypse would be. No fire, no screams, just the silent rewriting of reality's code. The universe wouldn't end in the traditional sense. It would become something else entirely, with new laws we can't predict. Would stars still shine? Would matter coalesce, or would the true vacuum birth a universe barren of structure, a wasteland where nothing ever forms again? The irony is palpable. We fear asteroids, black holes, and dying stars, but the greatest threat might be the vacuum of empty space itself. A single quantum hiccup could undo 14 billion years of cosmic evolution in an instant. And the most unsettling part, we might never see it coming. The universe's final act wouldn't be a bang, a crunch, or a rip, just a silent, flawless deletion, as if we'd never existed at all. The most unsettling thing about vacuum decay isn't just its destructive power, it's the silence. This apocalypse could already be unfolding somewhere in the cosmos, invisible and unstoppable, rewriting the laws of physics one light year at a time. Picture a chain reaction with no alarm. A single quantum event, perhaps near a dying star in a galaxy billions of light years away, triggers the collapse of the Higgs field into its true vacuum state. A sphere of annihilation begins expanding at light speed, its surface a wall of transformed reality. By the time its glow reaches our telescopes, it'll already be too late. The universe gives no second chances. What makes this scenario so plausible and so terrifying is the math behind the Higgs field. This invisible energy field permeates all of space, giving particles their mass. But some calculations suggest it might not be in its lowest energy state. Think of it like a valley surrounded by mountains. Our universe sits on a high ridge, stable for now, but a single nudge could send it tumbling into the deeper valley below. That nudge could be as random as a quantum fluctuation or as deliberate as a high-energy particle collision in some alien civilization's experiment. Once it starts, there's no undo button. CERN Large Hadron Collider has actually tested aspects of this theory. By smashing particles at near light speed, scientists probe the Higgs field stability. So far, the data suggests our vacuum is probably safe, but probably isn't the same as definitely. The margin for error is hauntingly slim. If the Higgs mass were just a few percent lighter, the universe would already be catastrophically unstable. That delicate balance hangs over us like a sword suspended by a thread. And here's the real kicker. If vacuum decay begins, we'd have no way to predict it. No shockwaves, no radiation spikes, just the sudden erasure of physics as we know it. One moment you're reading this, the next, the electrons in your device stop interacting with the screen. Atoms unravel, chemistry ceases to function. The very concept of you dissolves into a new set of rules we can't begin to imagine. Some theorists offer a grim consolation: the bubble might take billions of years to reach us. But others argue that if the Higgs field is unstable, the process could already be underway in our cosmic backyard. The universe is 14 billion years old, plenty of time for a decay bubble to have formed somewhere undetectable, its lethal edge racing toward us unseen. This isn't science fiction. It's a frontier of particle physics with real experiments and real stakes. The Higgs field's instability isn't just a doomsday scenario, it's a question about the fundamental nature of reality. Are we living on borrowed time in a cosmic house of cards, or is the universe more resilient than we fear? For now, the equations hold their secrets close. But every time a particle collider hums to life, we're rolling the dice not just for our planet, but for the fabric of existence itself. Black holes aren't just cosmic vacuum cleaners, they're the ultimate endgame for a universe that's run out of fuel. Picture a far future where every star has burned out, every galaxy has dispersed, and the only objects left are these gravitational titans, drifting through the darkness like hungry ghosts. This is the black hole era, a phase of the universe so long it makes the current age feel like a blink. Trillions upon trillions of years from now, black holes won't just dominate the cosmos. They'll be the cosmos, the last keepers of mass and energy before even they succumb to entropy's relentless pull. How did we get here? After all the stars exhaust their fuel and fade, after galaxies dissolve into scattered stellar remnants, black holes become the universe's primary actors. They'll feast on the remaining free-floating matter, planets, asteroids, rogue gas clouds, anything unlucky enough to cross their event horizons. Even in the cold emptiness of space, black holes won't starve. They'll merge with one another, growing larger and more massive, their gravitational grasp tightening as everything else vanishes. For an incomprehensible stretch of time, these monsters will reign supreme, their in-sky silhouettes the only landmarks in an otherwise featureless void. But nothing lasts forever, not even black holes. Thanks to Hawking radiation, a quirk of quantum physics near their event horizons, they slowly leak energy, shrinking over time. The bigger the black hole, the slower it evaporates. A supermassive one might take 10 to the power of 100 years, a number so vast it dwarfs the current age of the universe before it finally explodes in a final burst of particles. What's left? Nothing but a faint whisper of radiation fading into the infinite cold. The eerie twist: during this era, time itself becomes meaningless. The universe will be so old, so cold, that the intervals between black hole mergers or evaporations could be longer than the current age of the cosmos. Imagine civilizations rising and falling on planets orbiting these black holes, their entire histories unfolding in what amounts to a single cosmic heartbeat compared to the era's vastness. Yet even they won't escape the inevitable. Their black hole suns will vanish too, leaving behind a universe so empty it makes the heat death seem crowded. This is the paradox of black hole dominance. They're both the last survivors and the final gravediggers of the universe, devouring the last scraps of matter only to dissolve into nothing themselves. It's a fate that unfolds with glacial patience, a slow-motion apocalypse where even the mightiest objects in existence are reduced to fleeting sparks in the darkness. And when the last black hole fades, that's when the universe truly becomes a void, not just empty but forgotten. The last black hole in the universe won't go out with a bang, it'll vanish with a whisper. After swallowing the final remnants of matter and enduring for untold eons, even this gravitational behemoth will succumb to the slow leak of Hawking radiation. Picture it, a lone singularity, smaller than an atom yet heavier than a star, hovering in absolute darkness. Over unimaginable stretches of time, it loses mass particle by particle, shrinking until the moment it finally winks out of existence. The grand finale, not an explosion, not a collapse, just a fleeting burst of energy, a final sigh as the last organized structure in the cosmos dissolves into a sea of photons and leptons, particles so light they barely interact with anything at all. What's eerie is how quiet this ending would be. No observers, no fanfare, just the last flicker of warmth in a universe already cold beyond comprehension. The photons released in that final instant would travel forever through an infinite void, never striking another object, never being observed. They'd stretch into longer and longer wavelengths, their energy fading until they blend into the background hum of a lifeless cosmos. Even time loses meaning here. Without massive objects to warp space-time, without events to mark its passage, the universe becomes a static, featureless expanse, a canvas with no one left to paint on it. But here's where physics gets strange. That final burst of radiation wouldn't just vanish. According to quantum theory, information can't be destroyed, so what happens to all the data the black hole ever consumed? Some theories suggest it's encoded in those last particles, scrambled beyond recognition. Others propose that the information escapes into a baby universe, a hidden dimension branching off from our own. It's a haunting thought. The black hole's death might not be an end, but a doorway one will never be able to walk through. And then there's the unsettling question of what comes after. With no black holes left, no stars, no atoms, the universe enters the dark era, a phase so empty it makes the black hole era seem lively. Only the faintest particles remain, so spread out that they might as well not exist. Temperatures approach absolute zero and entropy finally peaks. This isn't just the end of matter, it's the end of change itself. No more collisions, no more reactions, just an infinite equilibrium where nothing ever happens again. Yet even in this bleakness, there's a twisted sort of beauty. The last black hole's death marks the universe's final act of transformation. Everything that ever was, every galaxy, every civilization, every quark has been reduced to its simplest, most elemental form. The cosmos began in a fiery singularity, and in a way it ends with one too, not with a collapse but with an evaporation, not with a scream but with a sigh. And then only the darkness remains. Protons have always been the universe's reliable building blocks, stable, unchanging, the bedrock of matter itself. But what if even they aren't eternal? Enter proton decay, a slow-motion apocalypse where the very atoms holding you together could one day unravel. This isn't science fiction. According to grand unified theories, attempts to merge the fundamental forces of nature, protons might not last forever. Over timescales so vast they make the age of the universe look like a blink, these particles could spontaneously break apart, dissolving matter into pure energy and leaving behind a ghostly haze of subatomic debris. How long would it take? Current theories suggest a proton's half-life could be around 10 to the power of 34 years, a number so large it's practically meaningless to human minds. To put it in perspective, if you watched a mountain-sized block of iron waiting for a single atom to decay naturally, you'd have better odds of seeing it happen before a single proton in your body vanished. Yet, given enough time, even these odds add up. In a universe old enough, every proton would eventually succumb, their quarks, the tiny particles bound inside them, ranging into lighter, unstable particles like pions or positrons before decaying further into photons and neutrinos. The result, a cosmos where solid matter, rocks, planets, even your own bones, slowly evaporates into faint trails of radiation. Scientists aren't just speculating. Experiments like Japan's Super Kamiokan, a colossal underground tank filled with 50,000 tons of ultra-pure water, have spent decades hunting for evidence of proton decay. By monitoring the water's molecules for flashes of light caused by rare proton disintegrations, researchers hope to catch this elusive process in action. So far, no definitive signal has appeared, but the search has already ruled out some grand unified theory models, pushing the proton's minimum lifetime even higher. The fact that we haven't seen it yet doesn't mean it's impossible, just that protons are even more stubbornly stable than we thought. The implications are staggering. If proton decay is real, then even the most durable remnants of the universe, white dwarfs, neutron stars, black holes aside, would eventually dissolve. Picture a future where not even dust survives, where every speck of matter has flickered out of existence, leaving behind a sea of particles too weak to form anything new. It's a more thorough erasure than even the heat death, where protons at least persist in some form. Here, the universe doesn't just cool down, it vanishes from the inside out. Yet there's a twist. Some theories suggest proton decay could be the key to understanding the universe's deepest symmetries. If protons can decay, it hints at a hidden connection between the strong nuclear force that binds them and the electroweak force governing radioactivity, a glimpse of the unified physics that might have ruled the cosmos in its first split second of existence. In that light, proton decay isn't just an end. It's a whisper from the birth of everything, a clue etched into the fabric of reality itself. What does that mean for us? For now, nothing. The timescales involved are so incomprehensibly long that humanity, Earth, even the sun will be ancient history long before a single proton in your body vanishes. But on a cosmic scale, it's a reminder that nothing is truly permanent, not even the particles that make up the stars. The universe might not just fade or collapse. Given enough time, it could quietly erase itself, one proton at a time. Galaxies, those glittering islands of stars we see scattered across the night sky, won't blaze forever. Imagine a future where the lights wink out one by one, not in explosions, not in violence, but in the quiet exhaustion of fuel running dry. This is the slow-motion apocalypse, a fade to black so gradual it's almost peaceful. But don't mistake its gentleness for mercy. The universe doesn't end with a roar here, it ends with a sigh. First, the stars themselves begin to falter. The most massive ones, the blue giants, are the first to go, burning through their hydrogen in a cosmic sprint before collapsing into neutron stars or black holes. Medium-sized stars like our Sun linger longer, swelling into red giants before shedding their outer layers and cooling into white dwarfs, dim embers that glow faintly for trillions of years. The smallest stars, red dwarfs, are the stubborn survivors, burning their scant fuel so slowly they might outlast every other object in the universe. But even they aren't eternal. Given enough time, think 100 trillion years or more, they too will dim, their nuclear furnaces finally sputtering out. As the stars fade, the galaxies they once illuminated start to unravel. Without new stars forming, the spiral arms lose their luster, becoming ghostly outlines against an ever-darkening backdrop. The remaining stellar remnants, white dwarfs, neutron stars, rogue planets, drift apart, their gravitational bonds weakened by the universe's relentless expansion. Galaxies, once tight-knit communities of billions of stars, dissolve into scattered orphans adrift in the void. But the true horror lies deeper. Even the atoms holding these remnants together won't last. If proton decay is real, the very building blocks of matter will eventually disintegrate. Picture a white dwarf already cold and dark, its atoms locked in a crystalline lattice. Over incomprehensible timescales, those protons decay, transforming the once solid sphere into a cloud of subatomic particles. The same fate awaits everything: planets, asteroids, even the dust between the stars. The universe doesn't just grow cold, it evaporates from within, leaving behind a haze of radiation so faint it might as well be silence. This isn't just an end, it's an erasure. No grand collapse, no dramatic rip, just a relentless fading until nothing remains but the faintest echo of what once was. And in that infinite stillness, time itself becomes meaningless. With no stars to mark its passage, no events to measure it against, the universe slips into a state beyond death, a silence so complete it forgets it was ever alive. Cosmic inflation is the engine that powered the universe's exponential expansion in its first fraction of a second, stretching space faster than light itself. But what if that engine suddenly stalled? Picture inflation not as a smooth, eternal process, but as a fragile bubble, one that could pop without warning, sending shockwaves through the fabric of reality. This is the nightmare scenario of inflation collapse, a phase transition so violent it rewrites the laws of physics in an instant. In most models, inflation ends gracefully, like a balloon settling after being inflated. But if it stops abruptly, think of a needle piercing that balloon. The energy driving expansion would be unleashed in a catastrophic burst. Space-time itself could recoil, crumpling like a sheet of paper thrown into a fire. The universe we know, with its finely tuned constants and stable forces, might cease to exist, replaced by something unrecognizable. Particles would lose mass, light would change speed, and the very rules governing chemistry and gravity could dissolve. The contrast with eternal inflation is stark. That theory suggests our universe is just one bubble in an infinite multiverse, with inflation continuing endlessly elsewhere. But in the collapse scenario, there's no safety net, no other bubbles to take our place. If inflation fails here, it fails everywhere. The multiverse isn't a tapestry of infinite possibilities. It's a house of cards, and our card is about to flip. What could trigger such an event? Quantum fluctuations, high-energy collisions, or even the natural decay of the inflated field, the hypothetical force behind inflation. Some theories suggest this collapse might already be underway in distant regions of space, its lethal frontier racing toward us at light speed. By the time we saw the warning signs, anomalies in the cosmic microwave background, sudden shifts in fundamental constants, it would already be too late. The implications are dizzying. If inflation collapses, it wouldn't just end the universe, it would erase the conditions that make universes possible. No new big bangs, no alternate realities, just a blank slate where physics itself is undefined. And the most unsettling part, we might never know what comes next. The collapse wouldn't leave survivors to ponder it. It wouldn't leave anything at all. If vacuum decay weren't unsettling enough, the Big Slurp takes cosmic annihilation to an entirely new dimension, literally. Picture our universe not as a standalone reality, but as a fragile membrane floating in a higher dimensional space, like a soap bubble drifting in an unseen wind. This is the realm of string theory's brains, short for membranes, where our entire cosmos might just be one slice of a much grander, multidimensional puzzle. And in this scenario, the end doesn't come from within, but from the collision or dissolution of these brains, wiping out existence in a way that makes the Big Rip look tame. The nightmare unfolds like this. In the higher dimensional bulk space beyond our perception, other brains might exist, parallel universes with their own physical laws, timelines, even versions of reality. Normally, these brains drift harmlessly, never interacting. But if two brains collide or one suddenly destabilizes, the energy released could cascade through dimensions, overwriting our universe's fundamental constants in an instant. Think of it as a cosmic computer virus, one that doesn't just delete files, but reformats the entire hard drive. Stars, planets, even space-time itself would reconfigure according to the new brain's rules, assuming anything recognizable remains at all. String theory offers a chilling twist. Some models suggest our brain might not be perfectly stable. Quantum fluctuations or interactions with hidden dimensions could cause it to slurp, a grotesque term for collapsing inward or merging with another brain. The effect, a wave of annihilation spreading at light speed, rewriting physics as it goes. One moment you're sipping coffee, the next the coffee no longer obeys electromagnetism, or your atoms cease to bind together. Unlike vacuum decay, which merely tweaks the Higgs field, the Big Slurp doesn't just change the rules, it burns the rulebook and replaces it with one written in an alien language. The most unsettling part, we'd have no warning. Higher dimensions are, by definition, invisible to us. The first sign might be a bizarre shift in particle behavior or a sudden tear in space-time, phenomena we wouldn't recognize until it was too late. And unlike other cosmic doomsdays, there's no after. No remnants, no radiation, just an abrupt transition into a reality where concepts like before and after might not even apply. Yet there's an eerie beauty to this idea. If the big slurp is possible, our universe might be just one iteration in an endless cycle of brane collisions, a fleeting configuration in a higher dimensional dance. Each collision could birth a new cosmos with different physics, some barren, some teeming with life. It's a twist on the multiverse theory where universes aren't just parallel but stacked, brushing past each other in ways we can't fathom until slurp, one brushes too hard. The irony is profound. We fear asteroids and dying stars, but the greatest threat might lurk in dimensions we can't see or measure. The big slurp isn't just an end, it's a reminder that everything we know, from quarks to galaxies, might be a tiny fragment of a reality far stranger than we've dared to imagine. And in that vast, hidden landscape, our universe could be little more than a soap bubble, gorgeous, fragile, and already beginning to pop. Neutrinos are the universe's ultimate ghosts, particles so elusive they pass through entire planets like they're not even there. Every second, trillions of them stream through your body without a trace. But what if these spectral particles turn deadly? In a nightmare scenario known as the neutrino-induced apocalypse, these harmless passers-by could suddenly gain mass, triggering a chain reaction that unravels the very fabric of matter. This doomsday hinges on a bizarre quantum phenomenon called vacuum metastability. Right now, neutrinos are nearly massless, barely interacting with other particles. But if something altered their properties, say, a fluctuation in the Higgs field or an encounter with an unknown force, they could suddenly become heavy. Once that happens, their increased mass would unleash a cascading effect. Every neutrino striking an atomic nucleus would transfer catastrophic energy, like microscopic bullets shattering their targets. Protons and neutrons inside atoms would destabilize, breaking apart into quarks and releasing bursts of radiation. One by one, atoms would disintegrate, starting a wildfire of destruction where matter itself comes undone. The Ice Cube Observatory in Antarctica, buried deep in the polar ice, is already tracking neutrinos with unmatched precision. Its sensors watch for the faint flashes of light produced when a rare neutrino collision occurs in the ice. So far, they've detected neutrinos from supernova, black holes, and even distant galaxies, but no signs of them gaining mass, yet the possibility lingers in the math. If a high-energy neutrino with just the right or wrong properties interacted in a specific way, it could theoretically initiate a phase transition. A single event could rewrite the rules, turning every subsequent neutrino into a catalyst for destruction. The terrifying part, we wouldn't see it coming. Neutrinos travel at nearly light speed, and by the time the first atoms started exploding, the wave of annihilation would already be unstoppable. Stars would flare violently as their cores destabilized, planets would dissolve into particle showers, and any life forms would vanish before they could process what was happening. Unlike other cosmic doomsdays, this one wouldn't just kill the universe, it would erase the building blocks that make existence possible. There's a twisted irony here. Neutrinos, born in the hearts of stars and cosmic cataclysms, are usually harmless byproducts of the universe's most violent events, but in this scenario they become the agents of its destruction. It's a reminder of how finely balanced reality really is, and how a single, invisible shift could bring it all crashing down. For now, the odds are vanishingly slim. But in a multiverse where infinite possibilities play out, somewhere, some universe might have already met its end this way. Not with a bang, not with a crunch, but with a whisper from a particle that no one saw coming. Our universe might not be alone, and that could be its downfall. Picture an infinite cosmic foam where countless other universes float like bubbles in a vast, unseen ocean. Each has its own physics, its own rules, its own destiny. Now imagine one of those bubbles drifting too close to ours, its walls brushing against the fabric of our reality. In that moment, everything we know, every law of physics, every constant of nature, could be rewritten before we even realize it's happening. This is the nightmare of false vacuum bubble collision, where contact with another universe doesn't just end existence, it replaces it. The math behind this scenario is as elegant as it is terrifying. According to bubble cosmology, our universe might exist in a metastable state, a precarious balance where the vacuum of space isn't truly empty, but filled with a latent energy field. It's like standing on a frozen lake where the ice seems solid, but one crack could send you plunging into icy depths. If a more stable bubble from another universe touches ours, that contact could trigger a phase transition, spreading outward at light speed. The boundary between the two universes would act like a cosmic virus, overwriting our physics with alien rules as it expands. Stars wouldn't explode, they'd simply cease to function, their atoms unraveling under new forces we can't predict. String theory adds another layer to this horror. In the brane multiverse model, our universe might be a three-dimensional membrane floating in higher dimensional space. Collisions between branes aren't just possible, they might have already happened. Some physicists speculate that the Big Bang itself was caused by such a collision. But if another brane slams into ours again, the energy released could be catastrophic. The resulting shockwave wouldn't just alter physics, it might erase dimensions, folding our reality into shapes beyond comprehension. Here's the twist, we'd never see it coming. The collision's wavefront would move at light speed, giving zero warning. One moment you're sipping coffee, the next the coffee no longer obeys the laws of chemistry. Gravity could invert, light might stop moving, or matter itself could dissolve into strings vibrating at frequencies our universe doesn't recognize. Unlike the heat death or Big Rip, this isn't an ending. It's a transformation into something utterly alien. The eerie beauty of this idea is its inevitability in an infinite multiverse. If countless bubbles exist, each with random physical constants, collisions aren't just possible, they're statistically unavoidable. We might live in a cosmic game of bumper cars where the other drivers are invisible until impact, and the scariest part, this could already be happening in some distant galaxy. It's light too far away to reach us before the wave does. Our doom might already be en route, written in physics we don't yet understand, racing toward us at the speed of causality. Yet buried in this doom is a strange comfort. If our universe can be overwritten, then perhaps others have been born from similar collisions. Death isn't an end, it's a reset button for reality. The atoms in your body, forged in stars, might one day become the raw materials for a universe where light moves faster, gravity pushes instead of pulls, or time flows backward. The cosmos doesn't mourn, it recycles, and in that infinite recycling, even annihilation becomes just another step in a cycle we're only beginning to glimpse. Quantum tunneling is usually a quirk of particle physics, a tiny electron slipping through an energy barrier it shouldn't be able to cross, or a radioactive atom decaying unpredictably. But scale this phenomenon up to cosmic proportions, and you get a doomsday scenario so bizarre it sounds like the plot of a sci-fi thriller. A killer singularity materializing out of nowhere, a black hole born not from a dying star but from pure quantum chance. How could this happen? Normally, forming a black hole requires crushing an enormous amount of mass into a tiny space. Think a collapsing star or colliding neutron stars. But quantum mechanics doesn't play by normal rules. At microscopic scales, particles can teleport through barriers, appear in two places at once, or pop into existence from empty space. Now imagine a fluctuation so extreme that random particles tunnel into the same infinitesimal point, packing enough energy to warp space-time into a singularity. Voila! A black hole is born, not from gravity's slow crush, but from quantum luck. Stephen Hawking explored this very idea in his work on primordial black holes, minuscule singularities that might have formed in the chaos of the early universe. But the same quantum instability could, in theory, create a black hole today. The odds astronomically low. You'd need a quantum fluctuation so precise it defies comprehension, like flipping a coin and getting heads 1,000,000,000,000 times in a row. Yet in an infinite universe with infinite time, even the impossible becomes inevitable. Here's where it gets unsettling. Unlike stellar black holes, which form predictably from dead stars, a quantum-spawned singularity could appear anywhere inside Earth, next to your coffee cup, even within the atoms of your body. If one materialized in your vicinity, you wouldn't just die, you'd vanish. A microscopic black hole would have the mass of a mountain compressed into a space smaller than an atom. Its gravity would be so intense that it would instantly start devouring everything around it, growing exponentially as it fed. Within minutes, it could consume the planet. But before you panic, consider the silver lining: Hawking radiation. Tiny black holes evaporate almost immediately, dissolving in a burst of particles before they can wreak havoc. A quantum-born singularity with the mass of, say, a bacterium would vanish in nanoseconds. The real danger lies in larger ones, those with the mass of a skyscraper or more. These could persist long enough to start accreting matter, snowballing into existential threats. The chilling takeaway: the universe doesn't need supernova or colliding galaxies to end us. Buried in the fabric of reality is a random, ruthless lottery, one where the grand prize is a black hole that rewrites the rules of existence. And the scariest part: there's no way to predict or prevent it. One day, space-time itself might just hiccup, and that could be all she wrote. Dark matter has long been the universe's silent partner, invisible, enigmatic, and holding galaxies together like cosmic glue. But what if this mysterious substance harbors a hidden danger? Imagine a scenario where dark matter's elusive properties shift unexpectedly, triggering a catastrophic implosion that drags the entire cosmos into a gravitational nightmare. This isn't just a thought experiment, it's a plausible doomsday lurking in the shadows of modern astrophysics. Unlike ordinary matter, dark matter doesn't interact with light or electromagnetic forces. We only know it exists because of its gravitational pull, which keeps galaxies from flying apart. But what if dark matter isn't as stable as we assume? Some theories suggest certain types could self-interact or decay over time, subtly altering its behavior. If dark matter particles suddenly became more prone to clumping, they could form dense knots of invisible mass scattered through space. These knots would act like gravitational landmines, warping the fabric of reality around them. Over time, they'd grow hungrier, pulling in nearby matter and other dark matter, until the entire universe becomes a patchwork of collapsing regions, each one a black hole in the making. Experiments like the LUX Zeppelin detector, buried a mile underground in South Dakota, are racing to uncover dark matter's secrets. By shielding sensitive instruments from cosmic interference, scientists hope to catch a fleeting interaction between dark matter particles and ordinary atoms. So far, the hunt has turned up empty, but that's part of what makes this scenario so unsettling. Dark matter could be far stranger than we've imagined, with properties that only reveal themselves when it's too late. The implosion wouldn't be instantaneous. At first, galaxies might simply drift closer together, their orbits subtly distorted by unseen concentrations of dark matter. Then, as the collapse accelerates, stars would be torn from their trajectories, plunging toward invisible gravitational wells. Entire galaxy clusters could vanish into these dark vortices, their light snuffed out as space-time crumples around them. The universe wouldn't end with a bang or a rip. It would be consumed from within, piece by piece, by the very stuff that once held it together. Here's the chilling twist: we might not notice until it's already happening. Dark matter's invisibility means the first signs could be subtle. A slight warping of light from distant quasars, an unexplained slowdown in galactic rotation. By the time telescopes spot the anomalies, the collapse could already be unstoppable. And unlike other cosmic threats, this one wouldn't leave a single corner of the universe untouched. Dark matter is everywhere, woven into the structure of reality itself. If it turns against us, there's nowhere to hide. Yet buried in this apocalyptic vision is a strange irony. Dark matter has always been the universe's quiet architect, the unseen hand shaping galaxies and guiding their motion. To think it could also be the agent of their destruction is a reminder of how little we truly understand about the forces governing existence. Every experiment, every detector, every theory brings us closer to unraveling the mystery, but what we uncover might rewrite not just science textbooks but the fate of everything. Hidden within the fabric of space-time could be defects so bizarre they make black holes look ordinary cosmic strings, theoretical cracks in reality left over from the universe's earliest moments. These aren't the strings of string theory, but something even stranger, ultra-thin, infinitely long filaments of pure energy, thinner than a proton yet denser than a mountain range. Stretching across the cosmos like invisible razor wires, they've been lurking undetected since the first fraction of a second after the Big Bang, and if one snaps, the energy released could rewrite entire sections of the universe in an instant. Think of cosmic strings as scars from a cosmic phase transition, like cracks forming in ice as water freezes. When the infant universe cooled, its fundamental forces separated, and space-time itself might have crystallized imperfectly, leaving behind these flaws. While most models suggest they'd be stable, drifting harmlessly through the cosmos, a catastrophic snap could unleash an unthinkable burst of gravitational energy. A single breaking string would send shockwaves rippling through space-time at light speed, warping reality itself. Galaxies in its path might be torn apart by tidal forces, stars flung like billiard balls, and any unlucky planet caught in the crossfire would experience earthquakes stronger than anything physics should allow. The proof might already be in the data. Gravitational wave observatories like LIGO have detected ripples from black hole mergers, but some unexplained signals could hint at cosmic strings vibrating or colliding. These events would produce a unique fingerprint, a sharp, singular burst unlike the gradual chirp of colliding black holes. If confirmed, it would mean these space-time defects are real, and their snaps could be ticking time bombs scattered across the universe. String theory adds another layer to the horror. If cosmic strings interact with higher dimensional branes, theoretical membranes from which our universe might be constructed, they could trigger a cascade of collapses like a thread snipping a taut fabric. The snap wouldn't just release energy, it might unravel the local laws of physics, creating zones where gravity reverses or time loops unpredictably. What makes this scenario uniquely unsettling is its stealth. A cosmic string could pass through our solar system right now, invisible and undetectable until the moment it fractures. There'd be no warning, no gradual buildup, just space-time itself splitting open in a flash. And unlike black holes or vacuum decay, this apocalypse wouldn't be universal. It'd be surgical, carving a path of destruction through the cosmos while leaving other regions untouched. A cosmic string snap wouldn't end the universe, it'd just edit it, erasing entire chapters of reality with the indifference of a broken pencil tip smudging a page. Yet buried in this chaos is a strange beauty. If cosmic strings exist, they're relics of the universe's birth, carrying secrets about how space-time first took shape. Their snaps wouldn't just be disasters, they'd be echoes of creation itself, reminders that even the fabric of reality is fragile, and that the universe's past might still hold the power to unravel its future. What if our universe isn't a physical reality at all, but a projection, a cosmic hologram flickering on some distant, higher dimensional surface? The holographic principle, a radical idea born from black hole physics, suggests exactly that. Space, time, even the stars above us might just be pixels in an unimaginably vast simulation. But like any system, glitches are possible. and if the code running our holographic universe corrupts or shuts down, existence itself could dissolve into digital static. This isn't science fiction, it's a serious theory grounded in the black hole information paradox. When matter falls into a black hole, what happens to the information it carries? Quantum mechanics says information can't be destroyed, but black holes seem to erase it. Physicists like Leonard Susskind and Gerard T. Hooft proposed a wild solution. The information isn't lost. Instead, it's smeared across the black hole's event horizon like a hologram, encoded in 2 dimensions rather than 3. Zoom out, and the same logic might apply to the entire universe. Every particle, every force, every moment of history could be data written on a boundary we'll never see. Now imagine a cosmic bug in that system. A single error in the holographic code could warp reality unpredictably. Gravity might flicker like a faulty light bulb, stars could blink out of alignment, or the very fabric of space might pixelate as the projection degrades. The most unsettling possibility, a total system crash where the simulation halts and every quark, every galaxy, every consciousness simply freezes or winks out of existence like a deleted file. The holographic principle isn't just about doom, though. It hints at something profound. If the universe is information, then reality might be more resilient than we think. Even if our hologram corrupts, the underlying data could persist, waiting to reboot in a new configuration. After all, in a digital cosmos, death might just be a temporary glitch, and rebirth a software update away. Yet the question lingers, who or what is running the simulation, and are we characters in the code or ghosts in the machine? The holographic universe doesn't just threaten annihilation, it redefines what existence even means. If we're living in a projection, then the end isn't just about physics failing. It's about the screen going dark. Time isn't just something we measure with clocks, it's the invisible river carrying everything from the birth of stars to the blink of an eye. But what if that river stops, not slows, not pauses, but vanishes entirely, leaving existence frozen in a single, eternal moment? This is the mind-bending possibility of time's end, a cosmic finale where entropy doesn't just sap the universe's energy, it erases the very framework of before and after. The key lies in entropy, the universe's slow slide into disorder. As energy disperses and matter decays, the arrow of time, the reason we remember the past but not the future, depends on this increasing chaos. But in the far, far future, when entropy peaks and the universe reaches total equilibrium, there'll be no more energy gradients, no more change to distinguish one moment from the next. Time, in essence, loses its meaning. Picture a wind-up toy winding down. First it moves, then it stutters, and finally it just stops. No ticks, no talks. Just stillness. Julian Barber, a physicist who dares to imagine a timeless cosmos, argues that time might not even be fundamental. In his radical view, what we perceive as time is just an illusion, a side effect of the universe's shifting configurations. Think of a flipbook. Each page is a static snapshot, but when you flip through them, you get the illusion of motion. Barber suggests reality might work the same way, a series of nows without any actual flow between them. If he's right, then the end of time isn't an event. It's the universe finally running out of new configurations to show. Quantum mechanics adds another twist. At microscopic scales, particles don't always obey a neat timeline. Quantum fluctuations can blur cause and effect, making before and after interchangeable. In a universe so cold and empty that only quantum jitters remain, time could dissolve entirely, leaving a froth of disconnected moments with no sequence to bind them. It's like a movie reel burned to ash. Each frame still exists, but there's no projector left to play them in order. But here's the real existential kicker. How do you define nothingness when time itself is gone? Emptiness implies space, and space requires time. Without time, there's no where or when, just a featureless void that can't even be called eternal, because eternity requires duration. Philosophers and physicists alike hit a wall here. Is it a state of pure potential, a blank canvas with no artist, or simply a question our minds, wired for time, can't truly grasp? The eerie beauty of time's end is its silence. No explosions, no collapse, just the universe pausing, like a held breath that never exhales. And in that endless stillness, the last flicker of consciousness, should any remain, might not even notice. After all, to notice change, you need time, and by then there'd be none left. What if the universe isn't just a vast expanse of space and time, but lines of code in an unfathomable supercomputer? The simulation hypothesis suggests exactly that. We might be living in an artificially constructed reality, a cosmic video game running on some higher dimensional hardware. And like any program, it could be shut down. Not with a bang, not with a collapse, but with the casual flick of a switch by beings we'll never see or comprehend. Nick Bostrom's trilemma lays out the unsettling logic behind this idea. Either civilizations never reach the technological capacity to create simulations indistinguishable from reality, or they choose not to run them, or here's the kicker, we're almost certainly living in one right now. The math is chillingly simple. If even one advanced civilization ever creates ancestor simulations, digital recreations of their past, the number of simulated minds would dwarf the number of biological ones. Statistically, the odds tilt overwhelmingly toward us being the simulations, not the simulators. The Fermi paradox, the eerie silence of the cosmos, might find its answer here. If we're in a simulation, the absence of alien contact isn't a mystery, it's a design choice. The creators might have limited the program's scope, leaving vast stretches of space empty to conserve processing power. Or worse, we're not the main simulation but a nested subroutine, a background process in some grander experiment, the universe's apparent fine-tuning for life. Just default settings in the code. Now imagine the shutdown. No warning, no gradual decay, just an instant termination. One moment you're reading this, the next the program halts. Reality freezes mid-frame like a glitched video game before dissolving into absolute void. No afterlife, no residual energy, just nothing. The simulators might not even bother saving their work. After all, why would you keep the data from a simulation you finished running? But here's the twist. Even if we're simulations, our reality is real to us. The pain, the joy, the starlight, it all exists within the framework of the program. In that sense, a shutdown isn't just an ending. It's the erasure of an entire cosmos, every memory and moment wiped as thoroughly as a deleted text file. The simulation hypothesis doesn't just threaten our future, it redefines our past. Every fossil, every galaxy, every heartbeat could be nothing more than variables in an equation. Yet buried in this existential dread is a strange hope. If we're in a simulation, death might not be oblivion, just a logout. And if the simulators are benevolent, maybe they'll hit save before shutting down, preserving our universe in some higher dimensional archive. Or perhaps they'll reboot it later, letting us live again, unaware we've done this all before. The simulation hypothesis isn't just a sci-fi trope. It's a mirror held up to our deepest fears and curiosities about existence. Whether we're code or flesh, the question remains, if the universe is a program, who's holding the keyboard, and when they're done playing, will they ever hit start again? The Big Bounce paints a poetic vision of cosmic rebirth, an endless cycle of universes expanding and contracting like a cosmic lung. But what if the next breath never comes? Beneath this elegant theory lies a chilling possibility. The bounce might fail, trapping our universe in a gravitational stranglehold with no exit. Loop quantum cosmology, a leading framework for understanding the universe's earliest moments, suggests the Big Bang wasn't a true singularity but a rebound from a previous collapse. In this model, quantum gravity prevents total collapse, creating a repulsive force that bounces space-time back into expansion. but this hinges on precise conditions, like a trampoline that only works if the fabric is perfectly taut. If quantum corrections aren't strong enough, or if dark energy's accelerated expansion alters the equation, the universe might crumple past the point of no return. Imagine stretching a rubber band until it snaps instead of springing back. The stakes couldn't be higher. A failed bounce wouldn't just mean a one-time collapse, it would erase the very mechanism of cosmic renewal. Instead of a new universe blossoming from the ashes, everything would compress into a terminal singularity, a dead end where not even time survives. Quantum gravity theorists debate how likely this is, but the math reveals fragile assumptions. For a bounce to succeed, the universe's density and geometry must align within razor-thin margins. Too much matter and gravity overwhelms quantum resistance. Too little and expansion dilutes the rebound's energy. Here's where observations clash with theory. The cosmic microwave background shows a universe strikingly flat and uniform, traits that favor endless expansion over cyclical rebirth. If dark energy's influence grows, as current data suggests, it could stretch space-time so thin that no bounce occurs, dooming the next cycle before it begins. The Big Bounce isn't just a hypothesis, it's a cosmic gamble, with reality itself riding on the outcome. Yet the most haunting question remains: if our universe is the first failed bounce in an otherwise unbroken chain, how many others came before? And if the cycle breaks now, does that mean it was never eternal to begin with? The silence of the cosmos offers no answers, only the cold void where the next universe should have been. Gamma-ray bursts are the universe's ultimate death rays, cosmic lasers so powerful they could sterilize entire galaxies in an instant. Picture a beam of energy packing more punch in 10 seconds than our sun will emit in its entire 10 billion-year lifetime. Now imagine that beam sweeping across space like a celestial scythe, boiling atmospheres and frying any life in its path. This isn't theoretical. We've detected these bursts from distant galaxies, their afterglows visible for weeks. But if one happened nearby, that's an extinction-level event written in gamma rays instead of asteroids. The most terrifying candidates are Wolf-Rayet stars like WR104, a ticking time bomb just 8,000 light-years away. These massive, unstable stars live fast and die hard, collapsing into hypernovas that unleash twin jets of gamma radiation moving at nearly light speed. If Earth happened to be in the crosshairs when WR104 explodes, the effects would be apocalyptic. First, the ozone layer would be obliterated within seconds, allowing deadly ultraviolet radiation to pour in. Next, atmospheric nitrogen would fuse into smog like nitrous oxides, blocking sunlight and triggering a global winter. Photosynthesis would collapse, food chains would unravel, and any surviving organisms would face a toxic, irradiated wasteland. The fossil record hints this may have happened before. The Ordovician extinction 450 million years ago wiped out 85% of marine species, and some scientists suspect a gamma-ray burst could explain its peculiar patterns of die-off. Unlike asteroid impacts, which leave iridium layers, or volcanism, which spreads gradually, a gamma-ray burst would selectively devastate surface life while leaving deep-sea ecosystems relatively unscathed, exactly what the geological evidence shows. What makes these bursts uniquely horrifying isn't just their power, but their unpredictability. We wouldn't see the beam coming. Light and gamma rays travel at the same speed, so the first sign of disaster would be the disaster itself. WR104 axis may or may not be aimed at us. Current measurements are frustratingly ambiguous, and even if we confirmed it was safe, thousands of other Wolf-Rayet stars lurk in our galactic neighborhood, any one of which could detonate tonight, tomorrow, or in 100,000 years. Yet there's a chilling irony here. These same catastrophic explosions forge the heavy elements necessary for life. The gold in your jewelry, the uranium in reactors, even the calcium in your bones, all were forged in the hearts of dying stars and scattered by hypernovas. The universe giveth, and the universe taketh away. One day, perhaps another gamma-ray burst will carve its signature across the Milky Way. The question isn't if it's when, where, and whether we'll be in its crosshairs when the universe decides to pull the trigger. Quantum entanglement is one of the most baffling and beautiful features of our universe, particles separated by light years influencing each other instantaneously, as if space and time don't exist between them. This spooky action at a distance, as Einstein called it, isn't just a quirk. It's the glue holding reality together at the smallest scales. But what if that glue suddenly dissolved? Imagine entanglement breaking down, not just in a lab experiment, but universally, sending ripples of chaos through the fundamental structure of existence. The fallout would be catastrophic. Entanglement isn't just about particles in labs. It's woven into the fabric of everything. Without it, atoms might lose their coherence, their electrons no longer properly aligning. Chemistry itself could collapse, bonds between atoms failing unpredictably. One moment, water is H2O. The next, it's a chaotic soup of unbound hydrogen and oxygen. Stars, held together by the delicate quantum dance of entangled particles in their cores, could destabilize, flickering out like candles in a vacuum. Even space-time, whose smooth geometry relies on quantum connections at the Planck scale, might fracture into a froth of disconnected bubbles. This nightmare scenario ties into one of physics' most heated debates, the black hole firewall paradox. When matter falls into a black hole, quantum theory says its information must be preserved, but general relativity says it's obliterated at the singularity. To resolve this, some theorists propose an inferno of high-energy particles at the event horizon, a firewall that burns incoming matter to ashes. But this violates entanglement, which should allow particles inside and outside the black hole to remain linked. If entanglement fails near black holes, firewalls might become real, and if that failure spreads, so could the fire. Reality's bedrock would burn away, not just at event horizons, but everywhere. The deeper horror, we might never see it coming. Entanglement breakdown could start in some distant corner of the cosmos, a crack spreading at light speed. By the time telescopes caught hints anomalous particle behavior, stars winking out in odd patterns, it would already be too late. The universe wouldn't end with a collapse or a rip, but with a silent unraveling, like a tapestry whose threads simply let go. Yet there's a haunting elegance to this idea. If entanglement defines reality's structure, its failure would reveal just how fragile that structure is. We think of the cosmos as vast and enduring, but its stability might depend on quantum threads thinner than thought, threads that, if severed, would leave not even ruins behind, just a blank slate where physics used to be. We often picture the heat death as a uniform fade to black, a cosmos cooling into perfect equilibrium like an ember fading in the void. But what if the universe doesn't freeze all at once? Imagine a slower, more fractured demise, where dark energy's invisible hand carves the cosmos into lonely islands, each doomed to their own private ice age. This is the Big Freeze eerie cousin, an apocalypse of isolation where regions of space are cut off not by distance, but by the unstoppable expansion of reality itself. Dark energy doesn't just push galaxies apart, it rewrites the rules of connectivity. Right now, it accelerates expansion gently, but some models suggest its strength could evolve over time. If it grows even slightly stronger, distant galaxies will eventually vanish from view, not because they've moved, but because the space between us stretches faster than light can bridge. Over eons, this acceleration would slice the observable universe into ever smaller patches, cosmic archipelagos drifting out of reach. Each island universe would be trapped in its own pocket of space, its night sky shrinking as neighboring regions redshift into invisibility. Here's where the horror deepens. Within these islands, the laws of physics might not just fade, they could fracture. As expansion accelerates, even the quantum fields underpinning reality could be stretched thin, like a rubber sheet pulled until it warps. In one isolated pocket, the Higgs field might weaken, reducing particle masses until atoms unravel. In another, electromagnetism could falter, rendering chemical bonds useless. Each island wouldn't just freeze, it would mutate, its physics twisting in ways we can't predict. The most tragic twist, intelligent civilizations trapped in these islands would witness their doom in slow motion. With no stars left to form, no new energy to harness, they'd watch the last light of neighboring islands blink out one by one, knowing their own fate is sealed. Even their radio signals, their final cries into the void, would never reach another listener. The cosmos wouldn't just die, it would forget how to grieve. Yet this scenario holds a strange silver lining. If some islands decay slower than others, or if their physics allows quantum tunneling to new vacuum states, tiny oases of structure might persist long after the rest have frozen. These survivors wouldn't be universes as we know them, more like flickering embers in a cosmic ash heap, but they'd defy the void just a little longer. The Big Freeze's greatest cruelty isn't the cold, it's the silence left behind when no one remains to remember the warmth. What if the universe isn't just shaped by consciousness? What if it requires it to exist? Beneath the cold equations of physics lies a radical idea from panpsychism. The notion that consciousness isn't an emergent property of complex brains, but a fundamental feature of reality itself, as woven into the fabric of existence as space and time. If that's true, then the death of consciousness could mean more than the end of observers. It could unravel reality at its core. This isn't mere philosophy. Quantum mechanics has long flirted with the role of the observer. In the double-slit experiment, particles behave differently when measured, as if choosing between wave and particle states based on whether they're being watched. Some interpretations suggest consciousness collapses quantum probabilities into definite outcomes. Take that further with the participatory universe idea. What if reality isn't just observed but constructed by sentience? Without it, the cosmic wave function might never fully resolve, leaving existence in a ghostly superposition where nothing truly happens. Now project this to the far future. As entropy grinds the universe toward heat death, the last stars burn out, the last black holes evaporate, and the final flickers of life, biological or artificial, fade into darkness. No more eyes to observe, no more minds to measure. In a panpsychist cosmos, this could trigger a cascading failure. Quantum events, no longer anchored by observation, might stagnate in unresolved probabilities. Space-time, lacking conscious interaction, could lose coherence like a dream forgotten upon waking. The universe wouldn't just grow cold, it would dissolve into ambiguity, its once sharp edges blurring into mathematical noise. The eerie twist, we might already see hints of this fragility. Dark energy's acceleration could reflect a universe relaxing as conscious structures decay, like a building whose scaffolding rusts away. Even the Boltzmann-Brane paradox, where a lone self-aware entity arises by chance, takes on new menace. It might not be a fluke, but a desperate quantum system trying to preserve observation at any cost. Yet the darkest implication is existential. If consciousness truly binds reality, then the cosmos isn't just indifferent to us, it's dependent on us. Every thought, every act of observation might be stitching the universe together moment by moment. And when the last mind winks out, there won't even be silence, just an unasked question hanging in a void that no longer remembers how to answer. What if our universe isn't floating alone in the void, but drifting toward an unseen neighbor on a collision course with annihilation? This is the Big Splat, a cosmic catastrophe where our entire reality slams into another universe, obliterating both in an instant. Unlike the slow decay of heat death or the shredding violence of the Big Rip, this is an ending written in the language of higher dimensions, where the very walls of existence crumble under forces we can barely imagine. At the heart of this scenario lies string theory's wildest idea, brane worlds, short for membranes. These could be vast, floating sheets of reality suspended in a higher dimensional space called the bulk. Our universe might be just one of many branes like pages in a book, each with its own stars, galaxies, and physical laws. Normally, these branes drift harmlessly, forever parallel. But if two branes wobble or ripple through the bulk, they could intersect, sending shockwaves through both worlds. The moment of impact wouldn't just destroy matter, it would rewrite the laws of physics at the speed of light. The math behind this comes from Randall-Sundrum models, theories proposing that gravity's surprising weakness compared to other forces might be because it leaks into extra dimensions. Picture our universe as a soap film clinging to the surface of a pond. Most particles like light or electrons are stuck to the film, but gravity can dip into the water below. Now imagine another soap film drifting toward ours. When they meet, the collision wouldn't just mix bubbles, it would unleash energies so extreme they make the Big Bang look like a firecracker. Here's the terrifying part: we might not see it coming. Extra dimensions are, by definition, invisible to us. A collision could already be underway in the bulk, its lethal shockwave racing toward our brane at light speed. The first sign, perhaps a sudden blue shift in distant galaxies as space itself contracts ahead of the impact, or a burst of bulk particles raining into our universe, defying known physics. By the time telescopes spotted these anomalies, the wall of annihilation would be seconds away, an unstoppable plane of energy rewriting reality pixel by pixel. What happens during the splat itself? Matter wouldn't just explode, it would unravel dimensionally. Atoms stretched between colliding branes might snap like thread, their quarks scattered into higher dimensional space. The very concept of location would break down as our three-dimensional world fused with the intruding brane. Stars, planets, even black holes could be smeared across dimensions like paint between two pressed canvases. And the aftermath, either a new, mangled universe born from the debris or absolute nothingness, as both branes dissolve into the bulk like sugar in hot tea. Yet buried in this chaos is a bizarre hope. Some models suggest brane collisions could be cyclical, each big bang the echo of a past splat. Our universe might be the latest iteration in an endless cycle of cosmic car crashes, each crash resetting the clock. But that's cold comfort when facing the raw physics of dissolution. The big splat isn't just an end, it's a reminder that our universe might be smaller, stranger, and more fragile than we ever dared to guess. Beyond the familiar dimensions of space and time, forces are moving in the dark, and one day they might come calling. Black holes might be the universe's ultimate paradox machines, cosmic shredders that swallow information but, according to quantum law, can never truly destroy it. For decades, physicists wrestled with this contradiction. If you toss an encyclopedia into a black hole, does the information vanish forever, violating quantum mechanics, or is it somehow preserved? The answer could rewrite reality itself, and the solution might be more terrifying than the mystery. Enter the firewall paradox. Imagine falling toward a black hole's event horizon. According to Einstein, you'd feel nothing special, just a gentle slide into oblivion. But quantum mechanics suggests a gruesome twist. As you cross the horizon, you might hit a searing wall of high-energy particles, a firewall that incinerates you into pure information. This isn't sci-fi, it's a desperate patch to preserve quantum rules. If information can't be lost, then the black hole must somehow encode it. But doing so might require turning the event horizon into a lethal boundary, contradicting relativity's smooth spacetime. Fuzzball theory offers a wild alternative. What if black holes aren't empty pits but tangled knots of cosmic strings, dense, fuzzy balls of vibrating energy with no sharp horizon at all? In this model, information isn't lost because it's woven into the fuzzball structure, like a book burnt but its ink preserved in the ashes. fall into one, and you wouldn't burn at a firewall. You'd merge with the fuzz, your atoms unraveling into the chaotic threads of the black hole's core. The most radical idea: black holes might reboot spacetime to resolve the paradox. Picture a computer crashing under conflicting commands, then restarting with a fresh operating system. Similarly, a black hole could reach a quantum tipping point where the contradictions between relativity and quantum mechanics force a localized rewrite of physics. The result: a microscopic Big Bang inside the black hole, birthing a new spacetime bubble with its own laws, one where information is preserved, but at the cost of annihilating the original black hole structure. The side effects would be catastrophic. If a black hole reboots, the energy released could trigger a gamma-ray burst visible across the cosmos, or worse, a chain reaction destabilizing nearby black holes. It's like knocking over the first domino in a galaxy-spanning sequence. Firewall or fuzzball, reboot or rewrite, the resolution to the information paradox isn't just academic. It's a ticking time bomb buried in the heart of every black hole, waiting to redefine the rules of existence. And when it detonates, the universe itself might need to choose between keeping its secrets or preserving its laws. The universe is vast beyond comprehension, dotted with hundreds of billions of galaxies, so where is everyone? The Fermi paradox's haunting silence might hide a terrifying possibility. What if intelligent life isn't just rare, but inherently self-destructive? Imagine civilizations reaching technological maturity only to accidentally, or deliberately, unleash forces that rewrite the fabric of reality itself. This isn't just sci-fi speculation. It's a chilling hypothesis known as the Great Filter, where advanced societies become architects of their own cosmic-scale annihilation. One version of this nightmare involves vacuum decay, an experiment gone wrong. Picture a civilization tinkering with particle accelerators 1,000,000 times more powerful than our own, probing energies so extreme they destabilize the Higgs field. A single misstep could create a bubble of true vacuum that expands at light speed, erasing physics as it goes. The grim irony: this wouldn't just doom the civilization that triggered it. The wave of destruction would sterilize the universe, leaving no trace of life anywhere. The silence we observe wouldn't mean aliens never existed, only that they all inevitably pressed the wrong button. But vacuum decay isn't the only existential trap. Consider black hole engineering, a hypothetical technology where advanced beings create microscopic singularities for energy or computation. One containment failure, and those black holes could fall into a planet's core, devouring it from within. Worse, if they're charged or rotating, they might not evaporate via Hawking radiation as predicted. Instead, they'd grow, swallowing stars, then galaxies, until the universe becomes a wasteland of drifting event horizons. The Fermi paradox's silence wouldn't just imply dead civilizations. It could signal a graveyard littered with their escaped experiments, the darkest twist. Some filters might not be accidents. A sufficiently advanced civilization, facing inevitable heat death, could choose to reboot reality via a controlled false vacuum collapse, a cosmic suicide button to spawn a new universe with fresh physical constants. Others might deploy black holes as weapons in interstellar wars, unwittingly dooming entire galactic clusters. In these scenarios, the Great Filter isn't just a hazard. It's a recurring feature of intelligence, a tragic flaw where curiosity or conflict inevitably leads to self-erasure. The terrifying implication is that silence isn't just absence, it's evidence. Every quiet star system could be a tombstone for a civilization that cracked the code of the universe, only to unlock its own destruction. And if that's true, the ultimate fate of our cosmos might not be written in the laws of physics, but in the hands of those reckless or desperate enough to play with them. The big silence isn't just emptiness, it's the echo of screams we'll never hear. After exploring 24 meticulously calculated cosmic doomsdays, we arrive at the most unsettling possibility of all, the end we can't predict. Despite centuries of scientific progress, 96% of the universe remains a mystery, its fate hidden in the invisible grip of dark matter and the enigmatic push of dark energy. These aren't just gaps in our knowledge, they're chasms vast enough to swallow entire theories. What if the true nature of these forces holds a doom so strange our current physics can't even fathom it? Think of dark matter as the universe's silent architect, its gravity sculpting galaxies into being without ever revealing itself. Dark energy, meanwhile, is the phantom hand accelerating cosmic expansion, an effect we observe but don't understand. Scientists compare it to diagnosing a patient by watching their shadow. We see the consequences, but the substance remains unseen. If these shadows conceal behaviors beyond our models, say, dark matter decaying into lethal radiation or dark energy suddenly flipping from repulsion to collapse, the universe could pivot toward an end no equation anticipated. History warns us against overconfidence. A century ago, physicists believed the universe was static and eternal until Hubble proved it was expanding. Then, in the 1990s, dark energy upended expectations again by showing that expansion was accelerating. Each revelation humbled our certainty. Now, as we probe deeper, we're forced to confront an uncomfortable truth. Our maps of reality are still missing continents. Could dark energy's acceleration spike exponentially, tearing atoms apart tomorrow? Might dark matter interact in ways that trigger a chain reaction of stellar explosions? The answer isn't just unknown, it's perhaps unknowable with today's tools. This uncertainty isn't failure, it's the frontier. Particle colliders hunt for dark matter particles, telescopes trace dark energy's fingerprints across ancient light, and theorists spin hypotheses ranging from extra dimensions to hidden universes. Yet for all our ingenuity, we're like sailors charting an ocean by its waves, blind to the creatures lurking beneath. The greatest cosmic threat may not be any scenario we've imagined, but one we haven't. And therein lies the paradox. The more we learn, the more we realize how much lies beyond the edge of our understanding. Perhaps the universe's ultimate fate isn't heat death or a big crunch, but something entirely outside our current physics, a twist so bizarre it rewrites the rules of endings altogether. Until then, we're left with a humbling thought. The cosmos might not just end in darkness, but in mystery. From the silent fade of heat death to the violent unraveling of the Big Rip, from quantum black holes blinking into existence to dark matter's invisible collapse, we've journeyed through 25 ways the cosmos could meet its end. Each scenario is a humbling reminder of how fragile our foothold in the universe truly is. We're adrift on a speck of rock orbiting an ordinary star in a galaxy that's just one of billions, all while suspended in a reality governed by forces we're only beginning to understand. The sheer scale of these existential threats could leave anyone feeling insignificant, like a flickering candle in a hurricane. But here's the twist: inevitability doesn't erase meaning. The universe may be doomed to fade, crumble, or tear itself apart, but we're here now. Every act of curiosity, every moment of connection, every leap of creativity is a defiance of the void. Think of it like building a sandcastle knowing the tide will wash it away. The temporary nature of the structure doesn't make the building of it any less beautiful. In fact, it makes the act more precious. Science doesn't just reveal our fragility, it arms us with awe. The same laws that predict cosmic doom also let us unravel DNA, decode the Big Bang, and send probes beyond our solar system. We're the universe's way of understanding itself, and that's a role worth embracing. So while the stars may fade and the laws of physics may one day rewrite themselves, the story of humanity is still being written. Let's make it a good one. Now, we'd love to hear from you. Which apocalyptic scenario chilled you the most? Was it the silent erasure of vacuum decay or the explosive finale of a big crunch? Drop your thoughts in the comments, and if you enjoyed this cosmic journey, hit subscribe for more mind-bending explorations of science and the universe. After all, the end may be out there, but the adventure is right here.